Good morning. I decided to do my project on the hysteresis effects on magnetic media in hard disk drives. I'll start with a brief definition of hysteresis. Hysteresis is a dynamic lag between the input and output in a system. Consequently, to understand the hysteresis system's behavior, we must know something both of the current state of the system and its historic behavior. Without the hysteresis effect, magnetic storage would not be possible. Hysteresis is a phenomenon which is prevalent in magnetic systems and has a vital and varying role to play in different mechanisms in the hard disk drive. I'm especially interested in the process of storing data by means of magnetic impressions on different material compounds. The hard disk drive comprises a read-write head which is accurately positioned above a disk or platter. The disk is constructed of magnetic compounds deposited on non-magnetic substrates. An electrical current is passed through the write head and an induced magnetic flux is created in the area below the write head. The magnetic flux affects the thin layer magnetic compound and leaves a magnetic imprint or orientation in the area below the write head. Data is stored in bits, ones and zeros. A one is stored in terms of a magnetic orientation between one local area on the hard disk and the next local area on the hard disk. A zero is recorded in terms of no change in the magnetic orientation between one local area and the next local area. To best interpret the magnetic characteristics of different compounds, we need to examine their MH loops, their magnetic moment against their induced magnetic field. So important properties of magnetic material are to be found directly from the hysteresis loop of that material. The first is the magnetic saturation. This is the maximum possible influence induced in the magnetic compound from a maximum induced magnetic field. The magnetic remanence is that level of magnetic flux which is retained once the electromagnetic induced field is completely removed. A higher remanence means a better material, a clearer signal output for data storage. The coercivity value, HC, is that level of induced field which is required to bring a magnetic medium from a point of saturation to a state of zero magnetic flux. The squareness ratio is calculated by remanence over the saturation. It's quite literally a measure of how square the loop is, and it reflects a medium's capacity to retain a certain amount of its magnetism. The squarer, the better. The switching field distribution is calculated by delta H over the coercivity. The switching field is a complex parameter. It's involved in magnetic reversal properties of individual nanoscopic bits on the thin film media. It's calculated by delta H over the coercivity. Delta H is the half maximal height of the derivative curve dndh. Another parameter related to the slope at the point of coercivity is S star. It is related to it's used in calculating maximal output signals for read processes. It's found by the derivative, the slope of the curve at the coercivity point equals to remanence over the coercivity by 1 minus S star. Now, the self-hysteresis loop that I have was taken from a sales brochure from an American company, Lakeshore Cryotronics from Ohio. They sell VSM magnetometer machines for testing magnetic properties. For instance, thin film magnetic medium, hard disk drives. The particular hysteresis curve that I looked at, I manually took the data from the curve and interpolated both left and right curves, used them as left and right bound in a general play operator that mathematical module that we used in class. I set an input function into this module that alternated inputs between minus 5,000 Oersted and 5,000 Oersted to accurately redraw the hysteresis curve as tested for a cobalt platinum alloy-based thin film magnetic medium. The limitations of this model are kind of twofold. I'll address that later. A quick one to note, though, is this flat line from an initial demagnetized state is not really accurate. It should rise from this demagnetized state on a first right basis and rise to saturation, then follow the major loop after that. In general, this singular loop model is an accurate reflection of magnetic characteristics of a medium. We use hysteresis loops to look at magnetic materials to see are they appropriate for use in hard disk drives. Things to look at: one, sufficiently high coercivity, where the hysteresis loop crosses the x-axis. We want a coercivity that is not too low. If it's too low, then it's prone. The data is prone to magnetic interference and possible inadvertent erasure. You don't want it too high either, because you want to be able to rewrite the data, and not have it permanent. I think a maximum nowadays is 6,000. Below 6,000 is fine. I think over 6,000 Oersted is not optimal due to limitations in magnetic right head materials at the moment. Second thing to look for is a large slope at the coercivity point. So you want a slope that's approaching 1. This gives a set and well-defined range of values within which you can reverse polarization or magnetic orientation in a medium from one pole to the other. So you can change that quite easily, well-defined. A third one is high enough saturation, high enough that your material is magnetically influenced, with a squareness ratio, a good squareness ratio, stating that the magnetic compound holds on to its magnetic influence. Some of these parameters for my sample loop, the cobalt platinum loop in the previous slide, with a saturation of 0.00294 electromagnetic units. It's acceptable, it's quite high, it's pronunciated from an old state. A remnant level of 0.00279 electromagnetic units. This is quite good again, because it's quite close to your full saturation. The material holds on to quite a lot of its magnetization, of the influence. That's reflected then in the SQR, the squareness ratio, which is a 0.948. Again, a very square loop, appropriate for hard disk drives. The coercivity of the sample is 1960 Oersted, which again, not too low to be prone to influence. Again, well below 6,000. A star running at point, come in. A star running at 0.999991. Let's stand up, play the rest. Stand for a second, I'll play the rest, and then you can fire ahead and do it again. Quick word on recording densities in the hysteresis loop. The capacities involved in today's hard drives are measured in bits per inch, circumferentially around the disk. This is achieved through a parameter called the transition length. The transitional length, which is the time it takes for a right head to change the magnetic moment of the magnetic media from one pole to the other. So it's the shortest distance within which to do that. It's given here by the formula. A is transitional length, twice the remnants over pi, divided by, again, these factors both have to be constant in order for this equation to be correct. This is the slope of the hysteresis loop, and this is the degree of induced field per distance, or change in induced field per distance. Increasing this capacity by hysteresis, we like that slope to get closer to 1, or the remnant value to decrease. Problems with the remnant value decreasing is prone to interference. Finally, up until now, I've had a single loop model. There's limitations to this single loop model. The first one, which I mentioned earlier, is that from a demagnetized state, or a first right This dashed line represents what should happen. My model has a problem with that. It doesn't reflect the first right situation. Secondly, in real world operations, the saturation points A and D are never really reached. There's a stochastic error in saturation levels on subsequent writes. So on every different write of a hard drive, and hard drives are constantly being written, rewritten, there's always a difference in saturation levels. A and D are never reached. So in an ideal situation, magnetizing force is pushed to saturation. When it's demagnetized, the curve is traced in the medium down to a remnants value of B. But in the real world, that curve is traced somewhere below the existing curve and down to a remnants value that's lower than B or higher than B, or it alters all the time. So in subsequent writes, there's always different loops. A multi-loop model is probably more effective at explaining hard drive operations in real life, but in reality, it's impossible to model that because you can't, there's stochastic errors, you can't really model them. So in terms of looking at properties, a magnetic medium's actual characteristics and properties for use in a hard disk drive, the single loop approach is the best. Thank you for your time. I'll be around for questions for a while, everybody.